Before we begin the discussion on implicit differentiation, let's first review our notation for derivatives. If I asked you to take the derivative of y equals x squared, you would probably at this point find this easy to do. It's 2x. What is this equal to? Well, the derivative, of course, which we can represent using y prime or dy dx. So when taking the derivative, the x squared becomes 2x and the y becomes y prime or dy dx. You can also think of this as applying the operator d dx to both sides of the equation y equals x squared. The right side becomes 2x and the left-hand side is just dy dx. This will be an important concept to remember during this section. To motivate implicit differentiation, let's look at this cute little curve. As a quick side note, this curve is an example of something called an elliptic curve. Elliptic curves have applications in cryptography. Notice that this curve doesn't pass the vertical line test, which means it can't be represented by a single function. However, we can still make tangent lines on this curve, and these lines have well-defined slopes. So the derivative, dy dx, still exists on this curve. Even though we cannot represent this curve with a function, we can represent it with an equation. The points on this curve satisfy the equation y squared equals x cubed minus 2x plus 2. We can then describe the curve using two functions. Y equals square root of x cubed minus 2x plus 2 is the top part, and y equals minus square root of x cubed minus 2x plus 2 is the bottom part. Y then is defined by x using several functions. In other words, y is implicitly defined in terms of x. We can use this fact and use the equation y squared equals x cubed minus 2x plus 2 to find dy dx. This is called implicit differentiation. So let's suppose we want to find dy dx of y squared equals x cubed minus 2x plus 2. What we do is just like what we did in the first example. We apply d dx to both sides of this equation. On the right-hand side, this is easy. By the power rule, this is just 3x squared minus 2. On the left side, since y is a function of x, we have a function of x squared. So we use the chain rule for this. We bring down the 2, leave the inside alone, then multiply by the derivative of the inside, which becomes dy dx. So we get 2y times dy dx on the left-hand side. Together we have 2 times y times dy dx equals 3x squared minus 2. To find dy dx, we just isolate this part using algebra. Dividing both sides by 2y, we get dy dx is equal to 3y squared minus 2 divided by 2y. This is our derivative. Notice that it has both x and y in the expression. We can find derivative values by plugging in points on the curve. For example, the point 1, 1 is on the curve, so the derivative at that point is 3 times 1 squared minus 2 divided by 2 times 1, which equals 1/2. At the point 1 minus 1, the derivative is 3 times 1 squared minus 2 divided by 2 times minus 1, which equals minus 1/2. Notice this matches with the sketch of our graph. At 1, 1, the tangent line is pointed upwards, and at 1 minus 1, the tangent line is pointed downwards. We can also find where the tangent line is horizontal by setting the derivative equal to 0. This would happen if the top is 0, which occurs when x is equal to plus or minus square root of 2 divided by square root of 3. Notice that there are 4 points on this curve with these x values. Finally, notice that when y equals 0, we get 0 in the bottom of the derivative, so it's undefined. Notice where this is in our curve. It's right on the bold part of the curve, so our tangent line would have to be vertical here.